Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. This time we're talking about predictive analytics, and this is a fairly regular session that we run at least once a quarter, where we talk about the discipline of predictive analytics and give some examples and try to put it within context for a lot of the people who are reading about all things to do with AI and machine learning, etc., etc. And very much to have a focus on the practicalities of developing a predictive analytics application. My name's Jonathan Quinn. I'm an analytics consultant at Smart Vision, and I'm joined online today by my colleague Rachel. Rachel will be making sure that everybody's logged in. If you haven't joined any of these sessions before, then it's just a few housekeeping points we like to make at the start. First of all, we record these sessions so you can listen to it again. Secondly, there is some slideware here that we show at the start just to put some context around things, and we'll email out a PDF copy to you after the session's ended. If you think it's particularly relevant for colleagues who aren't able to attend today, it might be possible for us to arrange a rerun on a private basis. Just send us an email afterwards and we'll see if that's possible. And with regard to asking questions, we're asking you to use the chat facility. Because at the moment we can't actually hear you. So if you use the chat facility, we'll try and answer questions as we're going along. But obviously, if we run out of time, we'll follow up with you offline. It's quite common for us to get a flurry of emails afterwards asking specific questions, and we do try to take time to answer those. So don't be afraid to contact us after the event if you like. A few words about Smart Vision and who we are. We are a technology organization that are specialists in advanced analytics, and by that we mean statistics, predictive analytics, data science, machine learning, all that kind of stuff. And we have a fairly deep heritage with regard to analytics generally within the technology company. We've all worked within the predictive analytics industry for at least 15 years. I've worked there 25 years for organizations like SPSS and IBM and SAS, if you're familiar with them, as an analytics consultant. And that means basically delivering projects and running training courses and doing technical support around a host of different applications for different sectors. It's very, very difficult to talk about a typical application at the moment. As we will see later on, there's actually quite a wide and esoteric collection of projects that we've worked on in all of these different industries over time. And usually every year we end up working on a project for a particular application that we've never worked on before. So things aren't changing in that sense. Things are always very, very specific and sometimes quite unusual applications. It's also worth pointing out that we are a partner to companies like IBM, so we do resell software and technology from IBM as part of an implementation, if you like. But we also work with open source technologies such as R and Python and Spark and things like that. If that's relevant to you, it's just worth bearing in mind. So anyway, let's get started. Let's start off talking about predictive analytics within this wider context of the fact that everyone's talking about analytics at the moment, really. As I say, you may have noticed there's quite a lot of interest in machine learning and all things to do with AI at the moment. And it's quite typical for us to get involved with applications which are billed as AI applications, which is somewhat bemusing for us because, it's not necessarily what we would describe as AI. I think one of the problems is that AI is covering a multitude of sins at the moment. It's everything to do with any kind of analysis of data followed by a recommendation or an output of some sort. And that's at best an extremely loose way of seeing artificial intelligence, if you like. And the same for machine learning. Machine learning is, for most people working within this industry, if you like, machine learning is simply a particular area of analytical capability. So I would take a very, very sanguine or liberal view of the term AI and machine learning, generally speaking. When we talk about AI and machine learning, when you actually start to dig down into, the underlying techniques and tools that people are using, when they're talking about algorithms, for example, you will hear them talking about things like predictive analytics. You hear them talking about, deep learning networks, things like uh, recommendation engines, um, time series analysis, that type of Bayesian estimation, and all that sort of stuff. Well, for us, that's really just predictive analytics. That's really what they're talking about when they talk about machine learning and uh, and AI. They're really talking about predictive analytics because all of these techniques and all of these approaches fall within the predictive analytics arena. There are, of course, certain specific AI-based applications like self-driving cars, for example, um, or even things like voice-to-text recognition, like Alexa or something like that, which are not specifically predictive analytics applications, but anything where we're analyzing data, for example, to generate a piece of output to help us make a decision, generally falls within the realm of predictive analytics. So, and to emphasize this point, actually, if you look up predictive analytics in Wikipedia, it basically makes one point. It makes the point that it is a variety of techniques. That's what Wikipedia has to say about it. Predictive analytics encompasses a variety of, it calls them statistical techniques. That's a bit specific, but let's say a variety of techniques from predictive modeling, machine learning, data mining, statistics, all that type of stuff that analyze current and historical facts in order to make predictions about future or otherwise unknown events. So when you think about all of these different approaches and the fact that some of them are classical statistics that we've been taught in school, and some of them are based on things like deep learning networks and based on these very sophisticated analytical routines where it's very hard to see what they're doing, and they're quite esoteric, and they come from a very specific discipline of computer science. They do have something underlying them, which they all have in common. It's not just the fact that they analyze data, because lots of tools analyze data. Rather, they generate new data. That's the thing that makes these things different, for example, from BI or from a visualization technology. The goal of a lot of these approaches is to create something that did not exist before in an organization's data pool, if you like, and that is new data in the form of estimates or predictions or recommendations. So you're seeing a screenshot here, for example, that shows new data that has been generated by an algorithm. In fact, it puts a dollar sign in front of each of these fields to indicate that it has actually been generated by an algorithm, so that you can see. And then it contains, as you can see, numbers and classifications, categories here, yes and no, and certain numbers. These numbers refer to likelihood or probability. So if you hold on to that notion, that the point about these techniques is to generate new data, then it's probably easier to take a step back and think about predictive analytics as a series of bullet points and to try to pick it apart. It's very hard to come up with a nice, simple definition for it, even though Wikipedia makes an attempt. But rather, the first thing we need to know about is that although it's called predictive analytics, ironically, it's not always about prediction per se. So, for example, predictive analytics applications could be used for anomaly detection. Anomaly detection isn't really a prediction, but it would identify an unusual event, for example, or an unusual transaction. So it's used as part of a fraud analysis, for example, or you're trying to identify clandestine activity in security applications. And it will actually produce a number for you. It will literally produce a column showing a score indicating how anomalous that behavior is. Another form of predictive analytics, which isn't necessarily predictive in nature, is segmentation. Segmentation is where you want to usually group similar people together based upon their behavior as customers, so that you can interact with them on a more appropriate basis going forward. Well, Again, the predictive analytics application will produce a new number or a new category indicating which category or segment that person belongs to, but it's not really a prediction. So predictive analytics really creates new data every single time, and these data take the form of estimates, segments, probabilities, forecasts into the future, recommendations, propensity scores, risk scores, anomaly classifications, likelihood values. That's their job. The job of these tools, whether they're machine learning or whether they're statistical in nature, whether they're 50 years old or whether they're only 5 months, developed only 5 months ago, is to create these new data. And that's very important because it turns out that the acid test of an analytical model is how accurate these new data are. If we look at, again, the screenshot, we can see these numbers being pushed out here by this system. We have no idea, however, if these numbers are just random. I mean, they might be utterly useless. So there has to be a way for us to actually look at the results that the algorithm, that the technique produces in predictive analytics, and then to say, well, how good is that? So the acid test is, how accurate, how well do they predict, how well do they estimate a likelihood, how well do they forecast in the future? And that's very much at the heart of assessing the worth of the predictive analytics application. But the usefulness of the application generally depends on the decisions we take as a result of these new data. And that's something which not many people spend perhaps enough time thinking about. When we talk about the dangers, for example, of machine learning, you see a lot of articles about the dangers of machine learning, or the limitations of machine learning, or the dangers of AI. Really what they're talking about is decisions from data. That's really what they're talking about here. And it's very easy, as we will see, to produce a model that shows predictions. It's a very, very simple thing to do. It's a little bit trickier to produce a model that has accurate predictions in it. And it's often very difficult to produce a model with predictions that tell you what to do, to tell you, what course of action you should take. That's often an entirely different problem that you've got to focus on. So it's something that we have to keep in the forefront of our mind when we're working through these examples. So how is predictive analytics applied out there in all of these different applications? Well, if you're working with retail, for example, predictive analytics is applied in things like, as we shall see, an example of basket analysis, and that's used where you try to identify what products are purchased together at the same time. The same thing could be used for, exactly the same approach can be used in things like predictive maintenance, where you're saying what sorts of components fail together at any point in time. So basket analysis is a specific term that says what do people put in their basket when they go shopping, but more generally speaking, it's a way of saying what things co-occur together, and that can be very useful because, one of the projects we've worked on, for example, we're trying to identify what component parts an engineer should take with them to a site before they leave the depot, if you like. Because if they don't have the correct component parts, they have to wait at the site for a delivery truck to turn up, and it can be very, very costly and time consuming. So using an approach like basket analysis, they can actually say, well, when this component part is needed, this other one's often needed, and this other one's needed as well. So the point is you can steal applications from one sector and apply it in a completely different sector. Then you have things like store clustering. People hear about segmentation, where they segment customers together and they say, okay, well, the customers belong to this particular segment BA here, which is bedrock, bedrock mail responders or something like that. Well, a lot of retailers are actually interested in clustering together their stores because they want to say, well, what type of store is this in terms of the behavior and the sales within that store, and it makes it easier for them to plan what type of, what sort of assortment goes into that store. And there's forecasting, of course. Forecasting could be literally at a very, very highly granular level. We have some customers that have built forecasts for pretty much every single product in the store. That means millions of forecasts every single week. And then in the financial world, you're going to hear things like credit scoring. This is a classic one. This is possibly the oldest application of predictive analytics you can get, really. Predicting whether or not somebody is credit worthy is a very old application. In fact, they use a technique from the 1930s to do that, which is logistic regression, actually using a very old technique to do it. But it could be fraud, it could be mortgage retention, it could be figuring out what other products you should sell to somebody. I find that when I go online, my bank is very keen for me to take up a personal loan. And it might be that I suspect that they're just offering that to me randomly, or because that's part of their main campaign that month or that quarter. It's probably not targeted at me. It's probably not based on a prediction, because there's a very low likelihood that I'm going to go for one, and secondly that they've been offering it to me for such a long time. And then even things like media companies, where you have things like Netflix or Now TV or Amazon, anything that produces digital media, for example, they're very interested in subscriber retention, because organizations spend a lot of money trying to get customers on board. And subscribers are particularly important, because when you're on a subscription to something, you have to tell them when you don't want to pay them any money anymore. So you basically got to tell them when you're no longer a customer. So that's important, because it means that the company knows the point at which you stop subscribing to them, such as a mobile phone contract. They know when you stop. Whereas for a retailer, it's not always clear when you have stopped shopping for them, shopping from their stores. So subscriber retention is a big application in any business where people are on a particular contract or subscription. And the things like feedback mining, which is basically looking at text analytics, for example, and saying, well, these are the things that people are asking for this particular month. And you have unusual applications like turf analysis. Turf analysis is used to identify the correct assortment of products, or the correct assortment of programs to show. So we've done some turf analysis for a radio station, for example, that was looking at what songs should be played for a particular market within a 1 hour slot. These are very specific applications, but you get a sense of how varied they are, even from one sector to the next. Insurance, of course, satisfaction modeling, identify satisfaction. Retaining customers is very important, because insurance is such an incredibly competitive area. There's fraud analysis, there's claim risk analysis. And water utilities are interested in things like customer profitability. Power utilities are also interested in that. Power utilities are often interested, for example, in trying to get customers to be dual fuel and direct debit. That's their most profitable customer group. So they're looking for opportunities to convert customers to both fuel, electricity and gas, and be direct debit at all times. But they have issues with problem resolution. Problem resolution for all companies, for all organizations, is costly. When certain things take 24 calls to sort out, and other things only take a single phone call, you're asking yourself, well, what's the difference between these two situations? And could we possibly mitigate that occurring? And then they have things like predictive maintenance, of course, where the data is not about people or about customers, but is about equipment. And equipment exhibits behavior which is sometimes hard to estimate or predict or account for. So predictive maintenance is used to address that. So that's within the commercial sector. When we look at the not-for-profit sector, some of the applications we've worked in, things like HMRC, we're looking at non-compliance and service quality. HMRC have inspectors, for example, they have tax inspectors, VAT inspectors that go out there, and they want to make sure that they're making good use of them. They don't want to send them out to carry out inspections which turn out to be effectively false, what you would call a false negative, or false positive, where you're saying, I suspect this business is misstating its VAT returns, and it turns out it isn't. That's a wasted opportunity, considering where you could have sent that tax inspector. So they use predictive models to identify, which businesses and which individuals they should be inspecting. But they also, to a much greater degree in the past few years, have tried to treat the taxpayers as if they're customers. So there's a greater emphasis upon getting the correct information to taxpayers. And they do things like cluster analysis, segmentation analysis. They do things like cross association analysis, which is a bit like basket analysis, identifying what sorts of pieces of information need to be served at the same time. And then in the charity sector, we have things like campaign response and customer supporter segmentation, identifying people who are high likelihood of being legacy givers. In higher education, there's a huge emphasis upon student retention and even acquisition of students. So last year we did a project for a large university where we were looking at a student acquisition, trying to get new students or the best students on board to get them to subscribe, get them to sign up for certain courses, because higher education has become so commercialized now that their universities are directly competing with one another. In healthcare, we've done projects like patient readmission, identifying patients who are likely to be readmitted to hospital following a non-elective stay, i.e. they've come into accident emergency and they've had a non-elective stay, they've stayed overnight, they've been discharged sometime after that, and then they've ended up back in hospital again, let's say within 30 days, and trying to identify what's going on there, and trying to identify patients that have a high risk of that occurring so that you can take action to mitigate it. And you've police, in the police we have lots of stuff around satisfaction modeling, outcome modeling around predicting the outcomes of particular investigations, crime prediction, of course, generally just saying what is the risk of a particular type of crime occurring in this location at this particular point in time. So you get a sense of the vast number of different applications out there. This is really genuinely quite a small sample of the sorts of applications that are out there where predictive analytics is being applied. More generally speaking, predictive analytics is applied where there is variation in an outcome and where people want to understand that variation better, and especially where they want to take action to influence that outcome. That's really what comes down to predictive analytics. And the thing that all of these applications have in common is that there is variation there. And in many ways, statistics is sometimes described as the science of variation. So how is this happening? Well, it's happening via a model that is being built. Okay, so when journalists talk about the algorithms, really what they're talking about are often models, really, and models are static patterns that are found in data. So predictive analytics is using historical data from people or incidents or equipment of some sort. And the sorts of factors that it will be using is things like, if we're looking at people-based data, looking at people's age, their gender, their average spend, the product category that they last shopped in, the region where they live, their tenure as a customer. And there's usually some sort of key outcome that exhibits variation that they want to influence. So it could be that they responded to an offer, they upgraded their contract, they defaulted on a payment, they recommended to a friend, they cancelled an appointment, they donated to a charity, or perhaps it's a system that has failed or a contract that has been renewed. And the goal here is to build a reusable model. A reusable model is effectively a pattern that has been found in that data. That is what a model effectively is. Now, this model takes the form, as I say, of a pattern or a formula. Sometimes there's a little formula that can be kicked out to you, that can be examined and tested. Sometimes the pattern itself is somewhat obscure. It's difficult to see what the model has actually done. But that is a very specific class of algorithms. There's only a particular set of techniques that do that. Most techniques that we would use produce a model that we can inspect in some fashion. And we think of the model, this pattern that's been found, as a physical object. It's probably a good way to think of it, rather than think of it as just some sort of piece of insight. It's actually a physical object that we can pick up and we can plug into other data. And by doing so, it will generate new results for us. It will generate data that will allow us to make a prediction. So we take the data from new data from individuals or incidents where the outcome is not known yet, but the individual's incidents include data such as age, gender, average spend, sentiment, tenure, time since last visit. And using a model that's based on the same information, we generate these new values that didn't exist before. We're generating estimates and likelihoods, or are more loosely described as predictions. So we can look at an individual, we can pass an individual through this pattern that the model represents in the data, and it will estimate or create a prediction or an outcome, such as people's estimated net promoter score or the probability of defaulting or their predicted lifetime value, or the chance of cancelling an appointment or something like that. So there's lots and lots of different outcomes we can generate from that. But the point about the model is to create these numbers. Otherwise, the model effectively is just a piece of insight that we've carried out against the data. So the critical point is, what do you do with that model? What are you actually going to do with these numbers that it generates? And it might be that you're just putting them out into a database. So you're simply saying, okay, I'm going to export a list of predictions. I'm going to export a list of customers with predictions against them. But you've got to ask yourself, to what end are you doing that? Are you doing it because you have an email campaign that you're going to use to target these customers? Are you trying to send out a physical piece of information or collateral or copy to them, which actually has a cost associated with it? Are you trying to serve information to them the next time they come onto your website? Is it actually some data that you're going to export to a handheld device of some sort, a professional device such as a camera-based system or a diagnostic system? Could it be something where you're actually sending out advice and recommendations and predictions to somebody in a call center who is having a conversation with a customer at that particular point in time, or a client at that point in time, where based upon the information that they're gathering, it's making recommendations? Or could it be that you're sending it out to an app that they're using? Maybe they're using a particular app. So this takes some thinking about, we're going to produce these predictions, and we're doing this for a particular purpose. We're doing this because we wish to reduce waste in some way, or wish to only offer products that are relevant to individuals, and therefore they're more likely to purchase them. Or we want to identify issues before they actually occur and mitigate them, such as missed appointments or something like that. But how we take action against that is critical. And this is what we refer to as deploying the model. The deployment of the model is when we take these numbers and we send them out into the real world so that we can take some sort of action. And until that happens, effectively what we've done is research. So let's look at a specific example here. And here we have a really simple little example here. We've got a person called Anna. She's 31 years old. And based upon some geodemographic information or some information about her purchase history, we estimate her income's around about somewhere north of £28,000 a year. On average, when she comes to our site, our website, she spends £26. She usually pays with her credit card, though she has in the past used her debit card. She isn't eligible for the discount offer this month because she hasn't spent enough money, or she hasn't been a customer for long enough. And in the last 6 weeks, she bought these 3 items in the last 6 weeks. Now, every time she's been coming onto the website, along with all the other thousands of customers that we have, what they've been shown is basically whatever we're offering at that month, whether or not it is relevant to them. Even if they've bought that product already, we're pretty much just showing them whatever the main offer and what the main campaign is. And we'd like to move to a point whereby we take account of her previous purchase history and demographic details in order to offer her something from a category such as home furnishing or cutlery or travel or something like that, which is relevant to her purchases. That is the issue at hand. So we have variation in her purchase history, and we want to take account of that variation, and we wish to make to surface to her, almost, if you think about in this example here, we're surfacing to a web. This is our deployment point. We're surfacing to a website. Could be that she's viewing it through her phone as well, but we want to show her something that's relevant. So how do we do that? Well, we start with data. So that's the first thing. So we get some data. And the data looks like this. So here's the data. This is connected to a database. And if I just show you what the data here for this particular individual on the customers, similar to Anna, looks like, we have some really simple data set here. I think it's only got 1,000 records. So it's a sample of 1,000 customers. They've all got different customer loyalty card ID or a cookie ID, if you like. And we have some basic information about how much money they've spent with us and what method they've used to spend money, and whether or not they're male or female, and whether or not we think they're a homeowner, and their estimated income and their age. But it turns out we're actually not going to use any of that data. What we're using is this purchase history data over here, which is just simply saying in the past 6 months, has this person bought anything from the textiles department? Have they bought anything from the travel department, the lighting or heating department, the electricals department, bathroom, home office, gardening, dining, bedroom, living room, kitchen? And that's what we're saying. We're basically saying, look, this looks fairly random here. You know, how common are these categories actually popping up? How often are these purchases being made? Well, we can see here that these little fields here that are basically trues and falses, where the larger bar is usually the false, saying this person hasn't made a purchase. So you can see here that, for example, we look at travel, double click on that. We can see that off all of the transactions, travel occurs across an 6-month period. About people purchase about 18% of the time they purchase something from travel, or 18% of the purchases have been something from travel. Of course, people purchase in multiple categories, and what we want is a sort of sense of, you know, of what the relationship is between these categories, so we can visualize that. We can use a particular type of chart. This is a chart called a web plot. It's a very simple way to visualize co-occurrence. We can use the same thing of co-occurrence for products that are purchased together. And it could be that this is looking at individual baskets in the supermarket, or it could be looking at, you know, in this case, a period of purchases over time, or it could be looking at something that's nothing to do with retail. It could be looking at, you know, component parts that fail together, or, you know, crimes that co-occur together, or, you know, even MOs that co-occur together. If you're looking at police sort of investigations, that type of thing. But here it's very simple. The thicker the line, the stronger the relationship. We can see there's a strong relationship here between home office, gardening, and electricals. There's also a strong relationship here between dining and kitchen, and a strong relationship between kitchen, living room, and textiles. And that relationship strength is really just based on the number of categories, or number of records that co-occur. So for example, here is a weak relationship between home office and bedroom. Well, only 54 times somebody has purchased something from home office, has purchased something from the bedroom department. But here, 173 times if they've purchased something from electricals, they've also purchased something from home office. And we can actually play around with these values, and we can change some of the thresholds here. If we don't like the default settings, we can go down here and we can use a little slider here. You can see we can just slide these values up and down and say weak links are anything below 88, and strong links are anything above 146 co-occurrences, if you like. So we can mask out the weaker relationships and see the stronger relationships. So this is a nice way for us to explore the data beforehand and to guess what sorts of recommendations our model might produce for us. And if we really want to formalize that and effectively turn that into, you know, a model, then we have a particular type of algorithm. If you look down here at them in this application here, the types of algorithms we have, there's lots and lots of different algorithms here. Look at all these different algorithms. And this is an association algorithm. This is one here called a priori. It's very much modeling without tiers. It's just basically going to do exactly what that chart did. We're using an IBM tool here. This is the IBM modeler tool. So this is a classic sort of predictive analytics workbench. If I run that, as I say, it's going to produce this model as a physical object. And the model's based on these 11 fields that are basically, you know, the purchase history. So when I double click on that, it shows me initially that it's found 44 rules. So these are 44 co-occurring rules. So you think about these are the thick lines, if you like, that's producing in the chart. And the first rule here is simply saying if they've got electricals and gardening, that's called an antecedent, if they've already purchased that. 17% of the time people have purchased something from electricals and gardening. And of that 17%, 87% of the time in the past 6 months, they've purchased something from home office as well. And then the next rule is home office and gardening. 18% of the time, 85% of the time, if they purchase something from home office and gardening, they purchase something from electricals. And then we have electricals and home office and gardening. So it's basically that three-way relationship that we were seeing initially here. Just basically showing this relationship here in this triangle of electricals, gardening, and home office. It's just showing that to us as a series of rules. And there's other things we can do here. We can switch on and say, well, show us how many actual instances are there, how many physical instances, and we can say, give us a rule ID number, just attach a little number to that so we know which rule is which. And down here, for example, we have a relationship between a dining and bedroom, and we have a relationship here between textiles and living room and that type of stuff. We also have a fairly strong relationship between, things like kitchen and things like cutlery, that type of stuff. So you see these strong relationships. You can see here it's found 44 rules. We have control over how many rules it finds. Actually, if I double click on this algorithm here, I can just go in and change some of the settings and say, okay, I'm going to give you the option here to say, okay, go down to a smaller group size, go down to like 2% of the data and hit run again. And this will produce more rules. And now it's got 244 rules because I've said you can go down to much smaller group sizes. And the result of that, it finds much more specific rules. Now, what's it physically producing when it does this? I said that all of these predictive analytics algorithms have to produce something that didn't exist before. Well, what this produces when I look at, if I attach a table node here to this nugget, if you like, this model nugget here, and say, what are you producing? What is it that you're bringing to the party, if you like? It's producing these values at the end. You see they have dollars in front of them, and these are the predictions. It's basically saying, offer this person dining, offer this person textiles. Why should we offer them textiles? Because there's a 57% chance that they'll go for textiles. On what basis are you doing that? On the basis of rule number 56, which I can look up inside here, and I can find rule number 56 if I just searched for rule number 56. It's in there somewhere. Where is it? It's rule number 56. You see textiles. This person's already bought gardening and living room, and there's a relationship between that and textiles. So that's what's driving that outcome that we're seeing there. And if for whatever reason we didn't want to use that, we didn't want to use that prediction, we could say, okay, what else have you got? Well, we've got this other recommendation, which is home office and textiles. Or we've got another one here, which is electricals and textiles. So it can make multiple recommendations because it produces multiple rules overlap. Sometimes you're going to get rows where there are no rules, there are no recommendations that are made, and that's simply because that purchase or that customer's history doesn't contain enough purchases within it to fire a rule effectively. So you can see how this is very important to organizations that want to identify what sorts of products get purchased together. But it's also useful for any sorts of piece of information. If you want to say, well, what sorts of information do people need when they come onto your website, when they're searching for certain things? What types of terms are associated with a particular type of outcome? And we can use the same approach as I say for things like whether or not component parts failure. It's basically just looking at co-occurrence. So this is a very specific type of application. We're calling it an association analysis, or it's sometimes called a basket analysis in retail. What about another application where we're actually trying to predict a specific outcome? So we've got another example here. We're trying to predict a specific outcome. And the specific outcome here is, if we just show you, is whether or not people will respond to an offer. So they've got an offer to redeem a voucher. And this is the offer down here. This is 43% of them redeem the voucher, 56% of them don't in this list of 43,000 cases. And you can see that the little bar charts here are just colored by people's likelihood to redeem that voucher. So when we look at age group, for example, here, look at age group, we can see that the older people are, the more likely to fall into the 0 group here, which is they don't redeem the voucher. So we would expect age group to be an important predictor of that. Now, if we wanted to predict or build a predictive model to predict whether or not people redeem their voucher, on the basis that using that model, we could then identify which people we should offer the voucher to in the first place, because there might be a cost associated with the offering. And there are lots and lots of different algorithms, as you can see, that we could use to build that. And it turns out that actually we can use something called an auto classifier. An auto classifier is where it tries out many different types of techniques and tries to choose the best technique that predicts that outcome most accurately according to your criteria. But the danger is that because this is simply a sample of 43,000 records, that that the predictions might not be accurate when we come to applying it to the real world. So there's something called training and testing models. So what that means is that if I connect this this data source up to this particular node here called partition, I'll just show you what happens when I do that. What that node does is it produces a new field that didn't exist before. And the new field is this field here called partition. And it just randomly marks the records as training or testing. That's all it's doing, just randomly marking them. So if I go in here and change the random number that generates that, I say generate a new random number and then run it again, there'll be a different stamp. There'll be a different records are then changed again, testing and training. And at the moment, if I look inside it, it's based on a 50-50 split. So 50% will be given the label training and 50% will be given the level testing, the label testing. And that means that when I connect up my auto classifier, which is going to make all of these algorithms effectively have a competition with one another to try and predict this outcome accurately, what it's going to do is it's going to only expose the records that have been marked as training. So only these records will be shown to the model building algorithm, and all the ones marked as testing will not be shown. So 50% will not be shown. But when it comes to selecting the best model, it will look at how all of the models performed on the testing group. So this is our test. This is the data we hold back from the model building algorithm. And it simply automatically says, okay, well, you know, this particular technique worked best on the testing group. And that way we avoid building models that are too specific to the sample data that we have. We try to build models which are going to predict well on unseen data, on data where it hasn't seen the result before. So if I run that procedure, it takes about a minute for it to run it. And you'll see a little box pop up in a second that says it's going to build 10 models. You can see the amount of time. And there are different criteria we can use. There's more than one way you can say, okay, select this based upon overall accuracy, or base it upon, you know, the speed with which you build the models, or base it upon profitability values. In other words, the model that wins there are different criteria we can apply to it. I think in this case it's a measure of accuracy. So it's saying, okay, try and find the most accurate ones, and the most accurate ones actually at predicting the outcome in the testing group. So that's what it's trying to do, is trying to predict the outcome in the testing group. So it says I've got 10 models to build. One has failed thus far, so it's dropped one out. One's effectively fallen. Now it's finished, and it retains by default the top 3. So it's going to show us first, second, third, if you like, of the different techniques that it's built. So when it gets to the end of this, we'll see another nugget. There's a nugget that's been built. If we look inside the original model building node, you can see here are all of the different techniques which are, see it's got U's next to it, which have been ticked here, all these different techniques. Some of them haven't been switched on because it just took too long to build. And you can see that, you know, when it comes to choosing the model, it says rank them by something called the lift value, and rank them using the test partition, the test group, if you like. So when I double click on this and I look inside here, it says I found 3 different techniques that predict this outcome. One's called this linear support vector machine. That is a true machine learning technique. Then there is a decision tree. This is a rule-based technique. This is a bit more transparent. And then there's a classical statistical technique. So it really encompasses all 3 areas of analytics. One's machine learning, one's rule-based, and the other's statistically based. And you can see why the overall accuracy is 79.6. This is 78.6, and this is 79.6 again. But it's actually choosing them based upon what's something called the lift value here. And in other words, there isn't a lot of difference between them. They're all pretty accurate, and we can actually see how accurate they are, because when I double click on this little chart here, it actually shows me how accurate that particular algorithm is, because it's saying, okay, this green group here in the group mark 0, these are the misclassifications, these are the mistakes, these are the errors in the model, because green means I predict you to be a voucher redeemer, and 0 down here means you did not redeem the voucher. So it's saying that effectively these are false positives, because it's saying, yeah, I think these guys are voucher redeemers, but they're not. And over here, it's saying, okay, I think these guys in the blue group here are people who aren't going to redeem the voucher, who aren't going to respond, if you like, to this offer, but in fact they did. So this is the false positive, and these are the false negatives. And that's actually quite a healthy result there. It's pretty accurate overall. If these were pure blue and pure green, that would be extremely suspicious. You do not want a model really that's 100% accurate, because it means that it's almost certainly bound to fail when you come to applying it to the real world. But you do have to have some sort of sense associated, a business sense associated with the cost associated with making mistakes. What is the cost with a false positive via a false negative? And that's really something that an analyst can't tell you. It's really something that's based on your business sense. You know, you have to think, well, what's the cost of making a mistake in this area? You can see here also that it says use, so it's actually ticking all 3 of these groups. And that means that it will use all 3 models here. So this is them all combined together to come up with a prediction. So when I connect up a output to this, so I connect up a table to this, I can see what this prediction is that it creates. And the prediction, just like beforehand, has a $sign in front of it. And this is the prediction. I predict this person to be a redeemer. So you can see this one's wrong. This is incorrect. Predict them to be a redeemer, but in reality they weren't. This one's correct. I predict them to be a redeemer, and they weren't. Why did it predict this person to be a redeemer? Well, this is in the testing group. This is the testing group. And it turns out there was a 64% chance that they would redeem the voucher. So it predicted them to be a redeemer. But in reality, this person here belonged to like the 30% that didn't redeem the voucher. So this model here, these scores that are produced, these likelihood scores, these probability scores, if you like, that are produced, they're being produced by these algorithms here, and the scores being combined together. Think of it like taking an average. It's actually called an ensemble score. And actually, if I don't like one of these models, so I say, actually, I can't use this because I can't explain it, I can switch it off. And if I want to look inside the models, I can double click on them and look inside them and say, okay, what were you doing there? So this one here shows me the model as a tree of rules, if you like. It's like a sort of family tree. It's called a decision tree. Later on this afternoon, we're doing a decision tree webinar where we explain exactly what these models do and how they work. But here it's using age group to split the data into responders and non-responders. Whereas over here, we have something like a logistic regression model. That's actually a statistical model. It's a statistical model that has a formula associated with it. So it's got like, it's got a certain equation that's used for it. This is the equation it uses, etc., etc. And then this is a linear support vector machine. That means it's a machine learning algorithm. But either way, it produces these predictions, and we can do various things here. We can assess the accuracy of the model using something like an analysis node here, and it will tell me how accurate these models are. So if I run that, it just gives me a little piece of output here saying that, yeah, on the testing group, it's about 79.58% accurate, so just about 80% accurate. And then it gives me a little report here telling me how many times it correctly predicted the zeros in the test group and how many times it correctly predicted the ones in the test group. And these 2 values here are the impurity, if you like, the model. These are the false positives and the false negatives, false positives and false negatives. So these are the error. 2,436 records were predicted to be zeros when in fact they were ones, and 1,900 here were predicted to be ones, i.e. responders, when in fact they were non-responders. And that's the error in the model. Now we could pick one of these models. We could say, actually, you know what, that's good enough for me. I'm just going to pick this one here. I'm just going to pick it out and say generate that model, and it just puts that model, flashes it over here. You see, this is this model, and I can then use that model to make predictions. And to show you how to do that, if I just go down here to this little example here, I've got an example of another decision tree model that I'm working with. This one here looks a bit like the one you've just seen already. Look in the viewer window here, you can see it looks like a decision tree. It's a sort of family tree in identifying who, as a series of rules, who will respond to this offer and who won't. And like all of these systems, it will produce, all of these models, it produces a prediction for us. And that prediction appears in the form of a probability. What's the probability of them being in group one, if you like, of being a responder? So if I take that probability value and I chart it, I can actually create a little chart of it. I can say, well, all the people at this end of the chart are the people who have the high likelihood of redeeming the voucher, and all the people at this end of the chart have the low likelihood of redeeming the voucher. But the thing that's interesting here is that this model is being applied to data. If I just show you the data here, where the outcome is unknown. In other words, these people haven't been offered. They actually literally haven't been offered. I'll show it again. They haven't been offered this voucher yet. So they've got the same information that the model was built on. So we know what products they purchased, but they haven't got an outcome variable. They haven't got a variable that says whether or not they redeemed the voucher because they haven't been offered the voucher yet. So all I got to do is connect up my model from earlier, and it generates for me the prediction of whether or not they redeem the voucher. And that's what allows me to take a decision, because I can then chart that. For example, I can take a chart of that particular likelihood to redeem the voucher, and I can say, well, you know what? I'm going to pick everybody whose likelihood of redeeming the voucher is above 60%, because this is actually quite an expensive voucher. Let's say it's pretty important, and I need to get it right. So I'm going to say anybody who's likelihood of redeeming the voucher, let's say greater than 60%, I couldn't meet 40%. I can actually right click on that and select that group. So it just creates a little selection for me. And if I look inside this selection, it's just going to say where the propensity value, call it a propensity value, is greater than 0.6. Yeah, I can even edit it and just say make it 0.6. And that will create for me a list of people's IDs and their likelihood to redeem the voucher. And all of the likelihood, the propensity to redeem the voucher is greater than 0.6. So how many records is that? Let's just see. We've been quite restrictive here. Let's see, it's 16,111 records that it has found with a likelihood of redeeming the voucher is greater than 60%. And if I then connect that up to a database, I can say, okay, punch out that list into a table in the database and call that list the spring voucher campaign. And that just punches out exactly this table that we saw earlier on into a database, and effectively allows me then to take action against that. So that is us using predictive analytics in reality. And in both of these situations here, whether or not we're looking at co-occurrence of categories that occurred together. In the case of Anna, we noticed that there was a strong relationship between kitchen and things like cutlery. So we'd probably end up, as she's bought 2 elements from kitchen, we'd probably end up offering her some from cutlery. But if we were looking at whether or not she's going to redeem a specific voucher, again, we'd come up with a specific number that says this is the likelihood that she would redeem this voucher. And in both cases, these models are producing numbers or values that allow us to make a better prediction. And that's very important. It's almost as if the algorithm itself is irrelevant, but the action that we take based upon the output, that is critical. So to help people guide them through this sort of process, there are different methodologies out there. This is the one that we tend to subscribe to. This is literally a documented methodology that tells you if you're going to do a predictive analytics project, maybe you should have a look at a good practice cycle, if you like, of how to do that. So there's this methodology called CRISP-DM that stands for Cross Industry Standard Process for Data Mining. And that basically means if you want to do a project, this is the roadmap for doing it. And it has its own website, which we maintain, called crispdm.eu, which you can go to and check out. And it will guide you through this process. And you can see the modeling part of it's actually, that's the technical bit, I guess, but it's actually a relatively small bit. Most of it's very, very practical in nature. And I can prove that effectively by saying, when we Smart Vision go to talk to a customer about a particular application, given that these applications could be anything from predicting recipe outcomes for a food manufacturer to understanding why mobile phone stations fail, or to predicting people's likelihood to renew a credit card or something like that. It could be literally anything. What we talk about is, why does the customer want to do this? Why this particular application rather than another application? What is it about it? Is it costly? Is it wasteful? Is it painful? Is it something that's mentioned in their annual report? Why this particular application? And then we start thinking, well, what would it take to make that work? So we're imagining the sorts of data. We may not know, but we're imagining the sorts of data we would need and the sorts of techniques we might need to make it work. But at this moment, at this stage, it's pretty vague understanding. We're just trying to imagine really what a row of data needs to look like to make that work. And then we're going to say, well, what does good look like? In other words, when we produce these predictions, I mean, the predictions might be 70% accurate, they might be 80% accurate, might be 90% accurate. We don't know. So how good do these predictions have to be in order for this to be regarded as useful, given the fact that any prediction that has error, how bad does the error have to be? Or is more false positives better than more than false negatives, or vice versa? Think about something like patient readmission. What happens if you come up with a list of 1,200 patients that are likely to be readmitted to hospital, but only 400 actually end up being readmitted to hospital? Are you wasting resources? So you need to focus on what good looks like. And the last thing we think about, well, how would we know it worked? If we produce these predictions, what changes are we going to make in order to assess their impact, so that people can say, because we did this, we saved X amount of money, or we increased level of satisfaction by this amount, or we decreased the clear up time, the resolution time by 20% or something like that. So these are the questions that we are asking ourselves. What we are not asking ourselves when we're going to do a project or discuss a prospective predictive analytics application is, we're talking about algorithms. We're never going to do that. That would be like a plumber turning up and looking to build a kitchen for you and talking about the types of spanners that they're going to use. And in many ways, it's almost a warning sign for customers that if they are talking to a supplier or to somebody who's going on about the technology that they're going to use a lot, or they're talking about the techniques that they're using a lot, it's not a good sign. You've got to ask yourself, well, why aren't they asking these questions? Because these questions are the questions that dictate the difference very often between success and failure. Most predictive analytics applications, AI applications, machine learning applications, fail due to very human, very practical reasons. They often, they relatively rarely fail due to things like model accuracy issues. It's much more to do with planning. So for advice to get started for our customers and prospective customers, is we advise them to make a plan and to think about, where would you have the biggest impact for the least amount of effort? And by the least amount of effort, we mean if you were able to, predict this outcome or estimate this outcome, and by 10% more accurately, what impact would that have? If you were able to reduce the amount of time by 20%, let's say, to resolve these issues, how would that impact it? So we're thinking about the things which are important to the organization. And we recommend that they consider looking at a proven methodology such as CRISP-DM, which is one out there. There's other methodologies, but that's the one that we tend to use. Don't get hung up on modeling techniques like deep learning networks or decision trees or regressions or anything like that. You've really got to look at the CRISP-DM process and focus on the start of the process. Why are we doing this? What are we hoping to achieve? And the end part of the process, which is, what are we going to do differently? How will we know if it's worked? That type of stuff. And then we ask them to think about the full data landscape. Don't just think in terms of the database or the data set even. Think about the wider data landscape that's out there, from spreadsheets that are floating around, contact systems, maybe free text data, in different departments. That could all be very useful. And think also about the practical impact of making a predictive analytics application work. It usually has some sort of impact upon somebody's job. They've got to do things differently. You know, there may be an impact upon IT because you're scoring a database, something like that, at 2 o'clock in the morning. You've got to get those people on board beforehand. Otherwise, the project application may fail due to very practical human reasons that have nothing to do with the technical aspects of it. Consider integration with other insight systems. If you've already got a BI platform, if you've already got a management information system, why not use the model scores and integrate things like propensity value or the estimate of time to resolve an issue, for example, depending on the application, with those systems in the same way that you would show profitability or show revenue or something like that. Why not show the output from the models and surface them, you know, through a visualization system? And then think about, you know, how will you know it's worked? Focusing on measuring the benefit, the response rate lift, the increased level of cross-sell, the revenue profit impact, the change in customer satisfaction, that type of stuff. And lastly, we recommend you check out our website because we've got a lot of material on there. We've got a lot of video material, we've got a lot of blogs, a lot of recorded webinars that talk about these particular issues in more detail. I do hope you find that useful. If you want more information about Smart Vision Europe, you can source software directly from us. That's what we do. It's one of the things we provide. And we will help with the selection and implementation of any analytical tools that you're looking at. We also offer a series of consulting and training services. We offer our own formal training as well as online recorded training. We've got quite a lot of deep experience with regard to things like classical statistics, for example. And we generally offer no strings attached advice and support to existing customers and prospective customers. So don't be afraid to drop us a line and ask us a question. In the meantime, thanks for tuning in this afternoon. We do look forward to you logging in again in the future, and I do hope you find that useful. Thank you very much.